Congratulations, you're on your final assignment. You are about to make an elevator simulator using an Arduino as a brain. If you've already used an Arduino in your own projects, you probably don't need this video, so feel free to skip it. If you have never used an Arduino before in your life, don't worry. It's very straightforward. The basics are easy to pick up. And if you've never coded a program in your life, if you've never programmed a computer before, don't worry. I'm going to hold your hand through all the basics. I'm not going to go into any deep detail until after the assignment is complete. We're going to design this together. We're going to write it together. We're going to go step by step. And then only after we have a working basic elevator project for you to show off will I embellish it a little bit and go into detail for some extra fun things that you can do. So the basic tour of the Arduino, specific to this assignment, is this. You have a USB port that connects to the computer, supplies power to both the Arduino and the circuit that we're going to be building with a few LEDs and buttons and resistors. The USB port is used both for sending the program from your computer to the onboard memory so that the Arduino can run it, but also, if you choose, you can have the Arduino talk back to your computer through the USB and print text on your screen, and if you send numbers, you can even use the basic plotter that's built into the Arduino IDE to show some pretty data. Once you've programmed your Arduino, the program is on the Arduino. It's not running on your laptop. That means that you can safely disconnect your computer, or shut down the software at least, and have the program still run on your Arduino. That means that, like I usually do, once you've programmed your Arduino, you don't have to connect it to your computer. You can connect it to things like a USB booster pack and make it completely portable. Some Arduinos will have a barrel jack, and as long as you connect something between 6 and 9 volts, pretty much any board will work just fine. Some boards can handle 12 volts, and some Arduinos can even handle 16 volts. But to be safe, keep it between 6 and 9. If you connect a power supply to the Arduino through the barrel jack, you're going to power the Arduino through a regulator that's on the board, which supplies 5 volts and 3.3 volts to what needs those voltages. If you connect it to the USB port, you're going to be directly connecting 5 volts to the power pins. There's 2 ground pins for 0 volts and 1 5 volt pin to supply your circuit and 1 3.3 volt power pin to supply circuits that need 3.3 volts, certain external components. We won't be using the 3.3. This header connects to the Arduino's analog input pins. If you connect a voltage to one of these pins from 0 to 5 volts, when you read it in your program, the Arduino will translate 0 to 5 volts into 0 to 1023. And you can use that however you see fit. We won't be using the analog pin for the basic elevator project, but I may come back to it. On this side of the Arduino are your digital I/O. These pins are general purpose I/O, meaning that depending on what your program tells the chip to use these pins as, they can be input pins, they can be output pins, they can be serial communications pins, and they can even, a few of them that are specially marked with a little star or a hash symbol, can even use the internal hardware timers to reliably give you simulated analog output with pulse width modulation. Specific notes are pin 0 and pin 1 on most Arduinos are used by the USB port for programming and communications with your computer. That means that anytime you're programming the chip or the chip is sending data back to the computer, you can't control the state of pin 0 and 1. Generally speaking, I don't connect anything to pin 0 and 1 unless it actually requires serial communications to something like a GPS or a digital analog converter. Digital pin 13 is also a little bit special because pin 13 on every Arduino I've ever seen has a built-in LED on the board that is controlled by 13. That doesn't mean that you can't use it, but I have seen pin 13 flash during downloads. So generally speaking, when you connect things external to the Arduino, try to avoid pin 0, 1, and 13 if you can. That leaves pins 2 to 12 to do whatever you want. And since we only need 4 push buttons, 4 inputs, 4 LEDs, 4 outputs, those 10 pins are more than enough. Now, I'm going to greatly oversimplify this. This is not really reality. But I'm just wanting to get across a few simple concepts. So, let's say we have the Arduino, and inside the Arduino are a bunch of transistors. And let's say we want to use arbitrarily pin 10 and pin 4 for our elevator circuit. And we're going to use pin 10 as an output to control an LED, and we're going to use pin 4 as an input to signal the Arduino that we want to call the elevator. So we have our current limiting resistor, and we have our LED. The Arduino has connections to plus 5 volts and to 0 volts, which we are going to represent with the ground symbol, GND. This symbol really just means that anything that you put on a schematic with this symbol is connected to this same point. So our power supply 0 volts is going to be connected to the ground. Our power supply 5 volts is going to be connected to 5 volts. And our LED is going to connect to 0 volts as well. And we're going to show that with the ground symbol. We have our load resistor and our LED. And I'm not going to be too specific about this, but if you divide 5 volts by 330, you will get about 15 milliamps, which is safe for the Arduino pin, even if there wasn't an LED that was dropping some of the voltage. Just a 330 ohm resistor or larger is enough to prevent damage to the pin. And 330 ohms happens to be a standard resistor size, so it's an easy choice. If you go down to the next standard size, this next smaller size of 220 ohms, it actually would be 23 milliamps, which is too much. So we are going to use some resistor value above 330 ohms. In order to turn this LED on, since we already have the 0 volt connection, we need to be able to connect pin 10 to 5 volts. Well, as we saw in the logic circuit earlier, if you wanted to connect pin 10 to ground, you remember the NOT gate, it would be through an NPN transistor that's connected to ground inside the Arduino, controlled by the Arduino. If this transistor was to turn on, it would be a logic low. But as we have already seen, if we connect both ends of a circuit to ground, then no current can flow and the LED stays off. To connect it to the high side, we need PNP transistor with the emitter connected to 5 volts, controlled by the microprocessor. And when we tell the microprocessor that we want the output to be high, it will turn on this transistor, which will allow 5 volts to be connected to output 10, powering our circuit and turning on the LED. At no time will the microprocessor turn on both of these transistors, because that would give us a short circuit. Now, from activity 3, you remember at the beginning when we were playing with the oscilloscope and we were talking about the concept of being solidly connected to 5 volts, solidly connected to ground, or not solidly connected to anything. If both of these transistors are off, then there's no conduction path to 5 volts and there's no conduction path to ground, and so the input is floating. That sounds like a bad thing, but it's not a bad thing, because what that means is that if both of these transistors are off, we can now safely connect something to the pin of the Arduino that will connect the Arduino pin to 5 volts or 0 volts, and we can detect the voltage on that pin. So in the Arduino, pin 4 also has a pair of transistors that could connect it to 5 volts and could connect it to ground. But since we're using it as an input, those transistors are simply not turned on. The microprocessor is always monitoring the input state of those pins and measuring the voltage that's on those pins. On an output pin, like pin 10, this transistor would be connecting to 5 volts, bringing the input to 5 volts, and the microprocessor could read 5 volts as a logic 1. If both transistors are turned off and those connections to 5 volts and ground are broken, we can use a push button. That's connected to plus 5 volts. To bring the voltage of pin 4 up to 5 volts and read a logic 1. The issue happens where if you're not pushing the push button, you are not solidly connected to 5 volts. So once again, input 4 is susceptible to noise. It's not connected to anything solidly outside. It's not connected to anything solidly inside the chip either. So how do we ensure a logic 0? By adding a pulled down resistor that is connected to 0 volts. And this does not have to be a big resistor. 10,000 ohms is more than adequate. So when the push button is not pressed, the resistor is connecting pin 4 to ground through a high value resistor, and the microprocessor sees 0 volts, and that's a logic 0. When we push the push button, this circuit is now solidly connected to 5 volts, and the microprocessor can read on the input of pin 4 5 volts and return to us a logic 1. Now, this is all good and fine as long as you code properly. And by code properly, I mean if you are using pin 4 as an input and going to be solidly connecting the input to 5 volts, you have to take care to not make pin 4 accidentally an output. Because if pin 4 was to be designated an output, then this transistor would turn on. Or this transistor would turn on. But by default, the default output state is low. So if that transistor was to turn on and connect pin 4 to ground, and you push the push button, now you have a solid connection outside the Arduino to 5 volts through almost no resistance whatsoever to ground. And again, you have a short circuit condition. You can also mitigate this hazard by adding a resistor to the input. And again, a 330 works. Just to put an upper limit on the current that is capable of flowing. Now, one nice thing about the Arduino is that unless you specifically tell it to treat one of these pins as an output, it is by default all inputs on all of the digital pins. Another nicety is that inside the microprocessor there is also the ability to connect a pull-up or pull-down resistor through code. This internal pull-down resistor actually removes the need, if you use it, to even have resistors connected to the outside world. So if we're using input pull-down or input pull-up, then we can ignore this resistor and ignore this resistor and just have a push button, simplifying our external circuit. So now let's create a very simple circuit with an LED and a push button and go through the code that's required to set it up and make the LED turn on when we push the button. Now, as stated earlier, you can use any of those digital pins except for 0 and 1 and 13 in any way you want. The way I am going to make this circuit, our elevator circuit eventually, is I'm going to interlace the LED for floor 4 with the push button for floor 4, and then the LED for 3, push button 3, 2, 2, 1, 1 on the breadboard. But initially we're just going to put the first push button and the first LED in place. So we have our Arduino. And we have pin 12. 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and I'm going to ignore 0, 1, and 13. Even though they're there, I'm just going to ignore them. Pin 12 is going to power our first LED. And I'm going to use 10K resistors because they don't need to be bright. Pin 11 is going to be our call button. And that's all we're going to build for now. Now, although it's not really necessary, I want this circuit to be very, very linearly constructed. I don't want wires going back and forth and zigzagging. I want it to be extremely clear on video what I'm doing. So I'm going to have the digital pins, which are here, feeding the circuit on the left side. The LEDs and the push buttons will be oriented along the middle. And the 5 volts and the ground on the other side of the push buttons will actually be coming from these rails on the opposite side of the breadboard. Since the power pins, the 5 volts and the ground pins, are on this side of the Arduino, I'm probably going to run jumpers from these pins to these two rails, and then additional jumpers from these two rails to these two rails, so that this is positive, this is negative, this is positive, this is negative, and we can connect our grounds and our 5 volts to either one in any mix that makes sense. I also tend to loosely color code my jumpers if I can. So I will use red for positive, black for negative from the power supply, and I will use orange or some other color that's not red and black wherever possible to be intermediate things like coming off of the I/O. So in this case, I'm going to take an orange jumper from pin 12 to a group of 5, and another orange jumper from pin 11, which is going to be our push button, to another group of 5. Our 10K current limiting resistor will go from one side of the board to the other, and the LED will complete the circuit from the resistor to the blue rail, like so. Now, depending on the push button that you use, you may have to do a little bit of testing and experimenting to determine which legs are connected together all the time and which legs are connected only when the push button is pressed. These particular push buttons have the legs sticking out the sides with no metal on this side or this side. This leg and this leg are always connected to each other. This leg and this leg are always connected to each other. So you want to have the jumper connected into this leg and have the jumper to the power supply, the 5 volt rail, not connected to this, but connected to this. Now, looking at this, it would be very annoying to push the push button because the jumper is in the way of my finger. So what I can do is, instead of having the jumper go to this side, I can take advantage and I can put the jumper over there going to this positive rail. So now when I push the push button, it's going to connect these two jumpers together on the same side, and I'll be able to stick my finger in from this side and just push the button and have everything out of the way. Personally, I really don't like these push buttons. They're very delicate with short legs, and sometimes you have to grab a pair of pliers to straighten out the legs, and they pull out of the breadboard way too easily. The push buttons that I specified in the Elmwood kit, if you choose to get it, are much nicer push buttons than these. For the demo, this will work. To get power, we will stick a jumper in this 4th hole, which is the positive 5 volts, and bring it over to the red rail, which is going to be our positive 5 volts on the breadboard. We will also grab a black jumper from the 3rd hole in that header, which is ground, and bring it over to the blue rail, which will be our ground. And also go from the blue rail on the left to the blue rail on the right. So now the red rail is all positive, and both this blue rail and this blue rail are connected to the Arduino's negative power supply. Let's go connect this to the computer and write a dirt simple program to turn on the LED